Dear 11th standard students, today in this video session we will discuss important topic in oscillation lesson. That the important topic is spring connected in series, then spring connected in parallel. First of all, we briefly see about springs connected in series. So before going to entering into this topic, we know about spring constant or force constant or stiffness constant. Let us consider one spring tied with the rigid support. This spring has a spring constant K or force constant K or stiffness constant K. This stiffness constant is a measure of stiffness of a spring. A load is attached with the lower end of the spring. Before load is attached to the spring, see the free end of the spring, that is the lower end of the spring. After connecting the load, so lower end of the spring is attached with the load. Extension is produced through a distance y, or elongation is produced through a distance y when load is attached with the lower end of the spring, where m is the mass of the load. Gravitational force experienced by the load of mass m, F is equal to mg. So due to the gravitational pull, the load is moves downward direction, then the spring is extension is produced through a small displacement y. During the displacement, restoring force is developed within a spring, that is F. The restoring force is developed within a spring is the same that of gravitational force experienced by the load is attached with the lower end of the spring. Then restoring force which is equal to gravitational force. So therefore restoring force F which is equal to minus Ky. So the negative sign which is indicates displacement or elongation produced or displacement produced by the spring or elongation produced in the spring due to the load of mass m, but downward direction, but the restoring force is exerted in the spring acting upward direction. So the negative sign, the restoring force and the displacement is in opposite direction, or restoring force or elongation produced in the spring is in opposite direction. So therefore force constant K which is equal to minus F divided by Y. For a given elongation produced in the spring due to the force F, restoring force stiffness constant or force constant is a greater value. Spring has a greater force constant, which indicates that the greater amount of force is required to elongate the spring. See, for a given elongation produced in the spring due to force, that spring possesses a stiffness constant or spring constant or more force constant. It requires a greater amount of force to elongate the spring, which means it is difficult to elongate the spring or it is difficult to compress the spring. If any spring has a more force constant or more stiffness constant, the spring is more stiffer, which means greater amount of force is required to elongate the spring or compress the spring. It's the same that of any spring has a lesser stiffness constant for elongation produced through a displacement y or through a distance y, lesser amount of force is required to elongate or compress the spring. For I have one spring, it is a stiffness constant is lesser means we need a less amount of force to elongate the spring or compress the spring. Anyhow, force constant or stiffness constant is a measure of stiffness of a spring. But now we are going to see the topic of spring connected in series. This is origin of coordinate axis, x axis, it is y axis. It is a rigid support. Take two spring. One spring has a spring constant K1 connected to end. Another spring has a spring constant K2. This end of the spring is loaded with the mass M. This is equilibrium position of mass or equilibrium position of load along the x-axis. This is x0. See, there are two springs as a different in force constant or different in spring constant K1, K2 connected in series. So top end of the spring, one end is connected with the rigid support, lower end of the spring is loaded with the mass or connected with the mass M. So equilibrium position of the mass initially x0 or x0. Now a small amount of force is applied on the mass towards the x-axis along this direction. What happens? See, you listen carefully. We apply the external force acting on the load of mass M along this direction. This is applied force. Now, both the spring elongation is produced. So, due to applications of external force acting on the load of mass M along this direction towards the x-axis, both the springs elongation produced. So, x1 is the elongation produced in this first spring of spring constant K1, then elongation produced in the second spring of the force constant or stiffness constant K2. Then the load of mass M is shifted from its equilibrium position towards the x0 through a distance x. So after applications of external force acting towards right side, the load of mass M is shifted from its equilibrium position to x. It covers a x displacement. So it covers a x displacement towards x-axis. Due to that extension is produced in both the spring. Extension is produced in the first spring x1, extension is produced in the second spring is x2. So therefore, the load of mass m is shifted through a distance x, which is equal to x1 plus x2. X which is equal to x1 plus x2. Equation number 1. So, during the elongation produced in the spring, restoring force is developed, which is equal to applied external force. So, therefore, restoring force is developed in the spring. Second spring is F. The same amount of restoring force is developed in the first spring also F. So, after applying the external force acting on the load of mass m towards right direction, restoring force is developed in both the spring with the same amount F in both the spring. But extension is produced in both the spring. It's different. So total extension is produced. How much distance is covered after applications of external force acting on the load of mass m from its equilibrium position is x. That x distance is covered by the load of mass m is due to extension is produced in both the spring x1 and x2. Extension is produced in both the spring is different, but the restoring force is developed in both the spring is same in spring connected in series. That's very, very important. So therefore, total force, restoring force is developed within a spring F, which is equal to minus K S into X. So therefore, after applications of external force acting on the mass of m, then the load of mass m is shifted towards a distance x. So therefore, total restoring force is developed. F is equal to minus effective spring constant connected in series, and the load of mass m is shifted towards right through a displacement x. Equation number 2. This formula is applicable. Now, both the spring is replaced by a single spring. The spring has a spring constant Ks. Next end of the spring is loaded with the mass m from its equilibrium position x0. After applications of external force acting on the load of mass m towards right direction, extension is produced within a spring through a displacement x. The same amount of displacement produced in the load of mass m through a displacement x. So, after applications of external force acting on the block of mass m, restoring force is developed within a spring. That restoring force is F. Then minus K is effective spring constant connected in series with the load of mass m is displaces through a distance x after applications of force F acting on the block of mass m towards x-axis. Yes. See, Ks is the effective spring constant connected in series. If both the spring is connected in series, both the spring is replaced by a single spring off with the spring constant Ks. This creates a effect is the same effect as that of both the spring connected in series. Restoring force is developed in both the spring is F. The same that of restoring force developed in the spring as a spring constant Ks is F. Then the mass of block is shifted towards right through a small displacement after applications of external force is the same that of after applications of external force F. the mass of block is shifted towards a displacement x. So restoring force is developed within a spring constant Ks. F is equal to minus Ks into x. Equation number 3. But displacement produced in the both the spring or extension produced in the both the spring is different. So, restoring force is developed in the first spring. F is equal to minus K1 x1. Okay. Then equation number 4. Restoring force is developed in the second spring. The same restoring force in series connection F is equal to minus K2 x2. Equation number 5. These students, from equation 4, F is equal to minus K1 x1, then x1 is equal to minus F divided by K1. Equation number 6. From equation 5, F is equal to minus K2 x2. x2 which is equal to minus F divided by K2. Equation number 7. F which is equal to Ks into x. Here x which is equal to F divided by Ks. Equation number 8. So from this equation 4, x1 is equal to minus F divided by K1. From equation 5, x2 is equal to minus F divided by K2. Then F is equal to minus Ks into x. From that equation, x is equal to minus F divided by Ks. So, how to calculate the total displacement produced by the point mass after applications of external force? Here, x which is equal to x1 plus x2. So here x value minus F divided by Ks, which is equal to x1 value minus F divided by K1 plus minus F divided by K2. So therefore minus F divided by Ks, which is equal to minus F divided by K1 minus F divided by K2 minus F divided by Ks, which is equal to 1 minus sign taken common out, minus F divided by K1 plus F divided by K2. So minus F divided by Ks, which is equal to minus F take common out, 1 divided by K1 plus 1 divided by K2. F get cancel, minus get cancel. 1 divided by Ks, which is equal to 1 divided by K1 plus 1 divided by K2. This is reciprocal of effective spring constant connected in series, which is equal to sum of the reciprocal of the spring constant of the individual spring. So from that equation we can calculate the effective spring constant. So 1 by Ks, which is equal to K1 plus K2 divided by K1 K2. So take the reciprocal. Effective spring constant connected in series Ks is equal to K1 K2 divided by K1 plus K2. This is important expression. if both the spring is connected in series, after applications of external force acting on the load, extension is produced in both the spring x1, x2, but the restoring force is developed within us. Both the springs remain same, is the same that of applied external force. So, after connecting both the spring, how to calculate the effective spring constant connected in series? Effective spring constant connected in series, Ks is equal to K1, K2 divided by K1 plus K2 Newton meter inverse. So, it is an important expression to represent the effective spring constant connected in series. See, if both the spring connected in series, effective spring constant connected in series, Ks is equal to reciprocal of spring constant 1 divided by Ks is equal to 1 by K1 plus 1 by K2. 1 by Ks is equal to K1 plus K2 divided by K1 K2. Then Ks is equal to K1 K2 divided by K1 plus K2. Now, n number of spring has a different in spring constant connected in series. How to calculate the effective spring constant connected in series? So 1 by Ks, which is equal to 1 by K1 plus 1 by K2 up to 1 divided by Kn. So therefore, reciprocal of spring constant connected in series, which is equal to n divided by therefore 1 divided by Ks, which is equal to summation of 1 divided by K I if I is equal to 1 up to I is equal to n. If all springs connected in series has an identical spring, has a spring constant K, then reciprocal of effective spring constant, identical spring has a spring constant K, then reciprocal of effective spring constant connected in series, which is equal to n divided by K. Effective spring constant connected in series, K is equal to K divided by n. So, after applications of external force acting on the load of mass m towards x-axis, then the load of mass m shifted to a small distance x. After that removal of external force, then the load of mass m oscillates from its equilibrium position from forward and backward. It will the load of mass m executes a simple harmonic motion. So how to calculate the time period of simple harmonic motion if both the spring connected in series? Generally, time period of oscillation T is equal to 2 pi square root of m divided by K. Now, here both the spring is connected in series, loaded with the mass m executing simple harmonic motion, then the time period T is equal to 2 pi square root of m divided by Ks. Then T is equal to 2 pi square root of m divided by effective spring constant connected in series, Ks value K1 K2 divided by K1 plus K2. Then time period of oscillation T is equal to 2 pi square root of m K1 plus K2 divided by K1 K2. Then what is the frequency of oscillation of load of mass m, which means frequency in simple harmonic motion if two springs connected in series? N, which is equal to reciprocal of time period of oscillation. So N, which is equal to 1 divided by T value 2 pi square root of M K1 plus K2 divided by K1 K2. The frequency of oscillation if two springs connected in series N is equal to 1 divided by 2 pi square root of K1 K2 divided by M K1 plus K2. This is another important expression. If two springs connected in series executing simple harmonic motion of the load of mass m, n is equal to 1 divided by 2 pi square root of K1 K2 divided by M K1 plus K2. Now we taken the ratio of elastic potential energy stored in the first spring and elastic potential energy stored in the second spring. You take the ratio, what will happen? See, generally elastic potential energy stored in the extension spring or compressed spring U is equal to half kx square. This is general formula. But in the first spring, elastic potential energy stored in the spring U1 is equal to half k1 x1 square. Then elastic potential energy stored in the second spring U2 is equal to half k2 x2 square. You taken the ratio of elastic potential energy stored in the first spring and elastic potential energy stored in the second spring. U1 divided by U2, which is equal to half k1 x1 square divided by half k2 x2 square. Half get cancelled. U1 divided by U2, which is equal to k1 x square divided by k2 x2 square. Equation number A. Already we know that if both the springs are connected in series, restoring force is developed in both the spring F, which is equal to applied external force. So restoring force developed in the first spring F is equal to minus K1 x1. Restoring force is developed in the second spring F is equal to minus K2 x2. So both the forces equal. So therefore force is equal. So therefore F, which is equal to F minus K1 x1, which is equal to minus K2 x2, minus get cancelled. K1 divided by K2, which is equal to x2 divided by x1. So this is equation B. Equation B, substitute in equation A. Equation B, substitute in equation A. So ratio of elastic potential energy stored in both the elongated spring U1 divided by U2 is equal to K1 divided by K2, which is equal to x2 divided by x1. Then x1 square divided by x2 square. So x2 get cancelled. x1 get cancelled. Then u1 divided by u2, which is equal to x1 divided by x2. This is a ratio of elastic potential energy stored in both the spring. Dear students, now we go to see another one topic, springs connected in parallel. Let me consider there are two springs as a different in spring constant. Is the first spring as a spring constant K1, second spring as a spring constant K2, connected alternatively like in the parallel. Both the lower end of the spring is coupled together, then commonly loaded with the mass M. See, both the spring as a different in spring constant K1, K2 connected in parallel. Both the lower end of the spring is coupled together, then commonly taken the connected with the load of mass M. Equilibrium position of the load of mass M before applying the external force X0. Now in our aim to calculate the, if both the spring has a different in spring constant connected in parallel, how to calculate the effective spring constant connected in parallel? Then then the system is executing simple harmonic motion, how to find out the time period of oscillation? Then how to calculate the frequency of oscillation? So see one by one. So after applications of external force acting on the block of mass M towards right direction or towards x-axis, what will happen? Both the spring extension produced or elongation produced in the both the spring is the same, but the restoring force is produced in the first spring is F1, restoring force is produced in the second spring is F2, but both the spring extension produced is remains the same. See the equilibrium position. The extension produced in the first spring is X with the spring constant K1. The extension is produced with the spring constant K2 with the same extension is X. Both the spring, the extension is produced with the same X with the different spring constant K1, K2. Then load of mass M shifted through a small displacement X towards the x-axis after applications of force F. So after applications of force M, that block of mass M is shifted towards a distance x towards x-axis, while due to both the spring elongation is produced with the same elongation x, but the restoring force is developed in the second spring is F2, restoring force is developed in the first spring is F1. So how to calculate the total restoring force is developed in the system? We can calculate the total restoring forces developed within a system F, which is equal to F1 plus F2, because total restoring force is developed within a system in the parallel combination, which is equal to the of applied external force. See, now replace the two spring connected in parallel by a single spring of a spring constant Kp. It will produce us the same effect as compared to the of two springs. So spring constant Kp loaded with the mass M to applications of force, it will displace us through a distance F, with that restoring force is totally developed within a spring F, because if both the spring connected in parallel is replaced by a single spring of spring constant Kp, it will create the same effect as that of this system. So therefore, how to calculate the total restoring forces developed within a system? First, we know that restoring force F is equal to minus Kx, but restoring force is developed in the first spring, F1 is equal to minus K1x, because extension is produced due to applications of external forces x. Then second spring F2 is equal to minus K2x. Equation 1, equation 2. But both the springs are replaced by a single spring of spring constant Kp applied with the same external force, then same amount of restoring force is developed within a spring which then produces same extension is x, because that block is displaces to a displacement x towards the right. So therefore here restoring force is developed within a spring of spring constant Kp F, which is equal to minus Kpx. Equation number 3. So therefore, total restoring force, restoring force F, which is equal to F1 plus F2. F value minus Kpx, which is equal to F1 value minus K1x plus minus K2x minus Kpx, which is equal to minus K1x minus K2x. So minus Kpx, which is equal to commonly one minus taken out, minus K1x plus K2x. So minus Kpx, which is equal to minus x, take common out, x, K1 plus K2. Minus x and minus x get cancelled. Kp, which is equal to K1 plus K2. So this is effective spring constant connected in parallel, which is equal to sum of the spring constant of individual spring. Effective spring constant connecting in parallel is greater value compared to that of spring constant of the individual spring connected in parallel. So effective spring constant connected in parallel is a greater value when compared to the any other greater value of spring constant in the parallel combination. Now, we are going to see the time period of oscillation if both the spring connected in parallel. T common equation T is equal to 2 pi square root of m divided by k. Here T is equal to 2 pi square root of m divided by kp. So T is equal to 2 pi square root of m divided by effective spring constant connected in parallel K1 plus K2. If both the spring has an identical spring constant Kk, here K1 which is equal to K2 which is equal to K, time period of oscillation 2 pi square root of m divided by K plus K, T is equal to 2 pi square root of m divided by 2K. Then frequency of oscillation. So frequency of oscillation n is equal to 1 divided by T. N is equal to 1 divided by T value 2 pi square root of m divided by K1 plus K2. So n is equal to 1 divided by 2 pi square root of K1 plus K2 divided by n. If both the spring has the same spring constant K1 which is equal to K2 which is equal to K, frequency of oscillation N is equal to 1 divided by 2 pi square root of 2K divided by M. So generally, if both the spring is connected in parallel, effective spring constant connected in parallel is greater value when compared to that of any other greater spring constant connected in parallel. In the contrary, if both the spring is connected in series, effective spring constant connected in series is lesser value than any other lesser spring constant connected in series. So it's a very, very important topic. When spring connected in series, what happens? Effective spring constant, what happens at time period of oscillation, what happens frequency of oscillation. Then same one, when both the spring connected in parallel, what happens? Effective spring constant connected in parallel, then time period of oscillation, then frequency of oscillation. Dear students, you carefully watch this video to learn the important topic of spring connected in series, then spring connected in parallel. Thank you, students.